So students, as we were seeing an example of cobalt ammonium complex, the central cobalt ion over here is having +3 valency, the +3 oxidation state, and it is attached with 6 ammonia ligands. So the ground state electronic configuration of cobalt 3 plus ion is 3d6, and so we are putting 6 electrons in these 3 orbitals. One will be the paired one, the rest of 4 will be unpaired electrons. Then we have Ns and Nd. So in case of a D2sp3 hybrid orbital or hybridization of cobalt 3 plus ion, the D2sp3 hybrid D2 and 1s and 3p orbitals are mixed together to give all 6 equivalent D2sp3 hybrid orbitals. So that's why we have these 6 hybrid orbitals. Now remember, we are using 2 of the d orbitals, 1 s orbital and 3 d orbitals. Now what remains is only 3 orbitals, and so when we are using those vacant D2sp3 hybrid orbitals, all the electrons are moved to form a pair, and so that's why remaining 3d orbitals are fulfilled with a pair of electrons. All 6 electrons are utilized over there. Now the inner unhybridized orbitals remains as it is. They have all 6 electrons as what required, and then the 6 pair of electrons from ammonia molecule enters into 6 unoccupied or empty D2sp3 hybrid orbitals, and so you get all the empty orbitals fulfilled with 2 electrons each with the lone pairs of ammonia molecule. And the 6 pairs of electrons, one from each ammonia molecule, occupy the 6 hybrid orbitals. Thus the complex has octahedral geometry, and it is a diamagnetic because of the absence of unpaired electron. So we know that there is no unpaired electron, so it will show a diamagnetic property. We have already seen what is diamagnetic, what is paramagnetic, and what is ferromagnetic as well in the earlier chapter. In the formation of this complex, since the inner d orbital, the 3d orbital, is used in hybridization, the complex, this particular complex is called as inner orbital or low spin or spin paired complex. So we are going to call them this kind of complexes as inner orbital complex or low spin complex or spin paired complex. So you can expect a question what all these kind of complexes are termed as. The paramagnetic octahedral complexes of, let's say, another complex, cobalt and 6 fluorine atoms. So this is actually 3 minus instead. So paramagnetic octahedral complex COF6 3 minus uses outer 4d in hybridization to give sp3d2 hybrid orbitals, and that's why it is called as outer orbital or higher spin or spin free complex. So let's see what is a hybridization scheme for COF 6 3 minus. This is a typical hybridization scheme for this particular complex, where the d2 orbitals are utilized from 4d orbitals for hybridization. The two d orbitals are used from 4d orbitals, and that's why you have the sp3d2 hybridization occurring over here. Your 3d orbitals are not utilized for hybridization, and that's why this particular complex is termed as outer orbital or high spin or spin free complex. In the tetrahedral complex, 1s and 3p orbitals are hybridized because it's a tetrahedral, right? So you have 1s and 3p orbitals, so sp3 hybridization happening to form 4 equivalent sp3 hybridized orbitals, and so the orientation will be tetrahedral. This is illustrated with the complex, particularly NiCl4 2 minus, nickel Cl2 Cl4 2 minus. This particular complex shows the tetrahedral geometry, and it can be explained with the hybridization of 4s and 3,4p, 1 4s orbital and 3 4p orbitals coming together, mixing together to form sp3 hybrid orbitals, and that's how you get a 4 sp3 hybrid orbital oriented in tetrahedral geometry. So the complex shape, molecular shape, is tetrahedral in this case. So nickel has +2 oxidation state, and that's why. So how do you find the +2 oxidation state? Remember, let's assume oxidation state of nickel's let's say X, then you have a chlorine oxidation state, definitely -1, so plus -1 into 4, and overall complex is anionic, so -2, and that's how X can be calculated further. X is equal to -2 plus 4, so that it gives us +4. So sorry, +2. So the oxidation state of nickel is +2. Here nickel is in +2 oxidation state, and the iron has the electronic configuration 3d8. The hybridization scheme, you can see over here, the 4s and 3p orbitals are coming together, mixing together to give 4 sp3 hybridized orbital, and that's how tetrahedral complex is formed by pairing with 2 electrons coming from 4 Cl- ions or chloride ions. Each in this particular complex, each chloride ion donates a pair of electron. The compound is paramagnetic. Now why paramagnetic? Because it contains 2 of the electrons unpaired. in unpaired condition. So there are two unpaired electrons, and that's why it shows a paramagnetic property. Similarly, now nickel carbon monoxide NiCO4 has a tetrahedral geometry. NiCO4 has a tetrahedral geometry. But it is a diamagnetic, since nickel is in the zero oxidation state. Here the nickel is in the zero oxidation state, and that contains no unpaired electrons. So the nickel, as this complex contains nickel in zero oxidation state, the nickel 3d orbital has all 10 electrons as it is, and that's why it is a diamagnetic, whereas NiCl4 shows a paramagnetic property. Here this shows a tetrahedral geometry, but it is a diamagnetic in nature. Now in case of square planar complex, the hybridization involves DsP2. The example is NiCN4 2-. Here the nickel is in +2 oxidation state, as we have seen over here as well. The nickel is in +2 oxidation state and has the electronic configuration of 3d8. The hybridization involves one d orbital and one s orbital with two p orbitals. So the hybridization scheme can be written in this way. This is typically orbitals of Ni2 remains over here. Now the hybridization involves one d orbital, because this unpaired electron goes into another orbital, 3d orbital, to pair it up, and so you get a 4 unhybridized 3d orbitals having paired electrons. And now we have one d orbital from 3d orbitals, one 4s orbital, and two of the 4p orbitals coming together to give 4 dsp2 hybrid orbitals. And this particular hybridization has a shape of square planar. And now after forming a complex with cyanide ions, the 4 cyanide ions gives or donates 2 electrons each to form a sigma bond in this hybrid orbitals, and that's how this particular complex will be a diamagnetic in nature, because all the electrons here are paired electrons, and that's why it shows a diamagnetic property. Now it's very important to note that the hybrid orbitals do not actually exist. This is like an explanation. In fact, hybridization is a mathematical manipulation of wave equations from the atomic orbitals, because it involves the Schrödinger equation solution for those electrons which are present in these different orbitals. So using Schrödinger equation, you can actually find the probabilities of electrons, or maximum probabilities of finding of electron in that confined orbital shapes or three-dimensional shapes, which we call them as orbitals. And so is just the mathematical manipulation of the electrons present in that three-dimensional shape. So the hybridization is just a concept to help you to understand and say that how these different molecular shapes are happening. It may not necessarily be true. We cannot actually see those shapes or the hybrid orbitals. Now, magnetic properties of these coordination compounds. The magnetic moment of coordination compounds can be measured by magnetic susceptibility experiments. The results can be used to obtain information about structures erupted by metal complexes. The critical study of magnetic data of coordination compounds of the metals of the first transition series reveals some different kind of complications. For metals or metal ions with up to 3 electrons in d orbital, like Ti3+, where you have d1 orbital, vanadium 3+, where you have a d2 orbital, d2 electrons, and chromium 3+, where you have d3 electrons. The two vacant d orbitals are very well available for octahedral hybridization with 4s and 4p orbitals. The magnetic behavior of these free ions and their coordination entities are quite similar. When more than 3 3d or electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for d4 Cr2+ and Mn3+, or d5 Mn2+ and Fe3+, or d6 Fe2+ or C3 cobalt 3+, cases, the vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 or 0 unpaired electrons respectively. The magnetic data agree with maximum spin pairing in many cases, especially with the coordination compounds containing d6 ions. However, with species containing d4 and d5 ions, there are complications. It may not agree always. So complexes like Cn3- or magnetic has a magnetic moment of 2 unpaired electrons, whereas MnCl6 3- has a magnetic moment of 4 unpaired electrons. See the contradiction? You have Mn Cn6 3- and MnCl6 3-. These are two complexes, and particularly MnCn6 3- shows the magnetic moment of 2 electrons, whereas the later one shows the magnetic moment of 4 electrons. Similarly, FeCn6 3- has magnetic moment of single unpaired electron, while F6 3- has a paramagnetic moment of 5 unpaired electrons. Cobalt F6 3- is a paramagnetic with 4 unpaired electrons, while cobalt oxalate 3- is a diamagnetic. This apparent anomaly is explained by valency bond theory in terms of formation of inner orbital and outer orbital coordination entities. Now, Cn6 FeCN6 and cobalt oxalate 3 minus are inner orbital complexes involving D2sp3 hybridization. The former two complexes are paramagnetic and later are diamagnetic. On the other hand, MnCl6 3 minus, FeF6 3 minus and cobalt F6 3 minus are outer orbital complexes involving sp3d2 hybridization and are paramagnetic corresponding to 4, 5 and 4 unpaired electrons. So using this valency bond theory, you can easily explain the magnetic behavior or magnetic properties of these complexes. However, there are few limitations to these valency bond theory. First of all, it involves the number of assumptions. We already know that valency bond theory is based on number of different assumptions. So there are number of different assumptions. Then second, it does not explain the color exhibited by coordination compounds. So coloring or colors of complexes are not explained. Then it does not give quantitative interpretation of magnetic data. So it does not exactly tell you the magnetic moment. It just shows you paramagnetic or diamagnetic based on the unpaired electrons, but it does not give exact magnetic data or magnetic moments as such. So that's again a drawback of this VBT. So we can write quantitative representation of magnetic data is not explained or given. It does not make exact prediction regarding the tetrahedral and square planar structures, where these are where the coordination number is 4. So this is something has an anomaly with respect to valency bond theory explanation. So the complexes involving coordination number equal to 4 is not predicted. Regarding tetrahedral and square planar. Then very important, it does not give any quantitative interpretation of thermodynamic and kinetic stabilities of coordination compounds. Remember, these coordination compounds, each of them, they have a typical stability or instability in solution or crystalline phase. So that kind of stability or instability is not explained using thermodynamic or kinetic properties with the help of this VBT, and that's why that can be a drawback. So kinetic and or thermodynamic is not explained. of what? The complexes. It does not distinguish between weak and strong ligands. So some of the ligands are strong ligands, some of the ligands are weak ligand, and some of them they are kind of a moderate ligands. They can sometimes be, based on the situation, they can act as a strong ligand. Based on the situation, they can act as a weak ligand. So this particular theory does not justify these strong and weak ligands. So it is not weak and strong ligands. And that's why use of this valency bond theory you can utilize to predict the structures, predict some magnetic properties, but not for all the interpretations like thermodynamic data or kinetic data. Then the stability of the complex and etc. So for that we have a crystal field theory which helps us at least to understand the complexation, like when complexation happens, how exactly the colors are interpreted, or why these complexes have a typical colors. That can be very well explained by a crystal field theory. So CFT, crystal field theory, is an kind of a alternative for VBT, at least in case of coordination complex. So crystal field theory is an electrostatic model which considers metal ligand bonds to be ionic, arising purely from electrostatic interactions between the metal ion and the ligands. So ligands are treated as point charges. They are not actually electron donating groups or something like that. They are simply treated as a point charges, or even the metal ions are also kind of a point charges. In case of anions and dipoles, in case of neutral molecules, the 5d orbitals in an isolated gaseous metal atom or ion have same energy, that is, they are degenerated. So all the d orbitals are assumed to be degenerated and they have same energy. This degeneracy is maintained if a spherical symmetry field of negative charges surrounds the metal atom or ion. However, when this negative field is due to ligands, either ions or negative ends of the dipole molecules like ammonia or water, in the complex it becomes asymmetrical and the degeneracy of d orbitals is lifted, or they are no more remain the degenerated d orbitals. It results in splitting of the d orbitals. Now they have a different categories energy wise. Some of them they are combined together as they are same energy, and some of them they are not combined, or they are separated basically. The pattern of splitting depends upon the nature of crystal field. So let's understand how the splitting of different crystal fields happen. So in a nutshell, I'll try to explain you how exactly this crystal field theory works. So the ligands, maybe ions or the neutral molecules like ammonia or water, they behave as a point charges, and the metal atom or ion which is at the center of the complex, it has a d orbitals, and those d orbitals are degenerated when there are no ligands attached to that particular metal atom or ion. The orbitals are degenerated. Degenerated means they are of same energy, as if like the metal atom or ion is in gaseous state. But when these complexing ligands approaches or attaches to that metal atom or ion, this degenerated d orbitals separates and their degeneracy is lost because of the charge balancing of due to this complexing ligands. Okay, so let's understand this in little further. The crystal fill splitting in octahedral coordination entities. So let's first understand octahedral coordination complexes using this crystal fill theory. In octahedral coordination entities with 6 ligands, in octahedral complexes you have 6 ligands for sure, that surrounds to the metal atom or ion. There will be a repulsion between the electrons in metal d orbitals and the electrons or negatively charges of that ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the dx2 and dx2 dy2 and dz2 orbitals which points towards the axis along the direction of ligands will experience more repulsion and will be raised in the energy, and dxy, dyz or dxz orbitals which are directed between the axis will be lowered in energy relative to the average energy in the spherical crystal fill. First of all, let's understand the shapes of d orbitals. We have already seen in 11th standard, but still once again we'll repeat, and the things which we are talking about can be explained. So these are different d orbitals. Remember, the dxy is remember this is x-axis, y-axis, z-axis, okay, of a Cartesian coordinate. The dxy orbital remains on this xy plane. dyz orbitals remains on this yz plane. But they are not relying on each axis. Very important. They are in between the axis. Okay. Then dxz orbitals relies on xz plane. They are also not on the exactly the axis, xyz axis particularly. However, dx square y square or dx2 y2 orbitals are on the x and y plane, or sorry, x and y axis particularly. Then dz2 orbital is also on the z axis like this. Alright, but there is a ring here over here which actually cross sects the x and y axis as well. Mostly the dz2 orbital is more or less relies on the z axis, whereas dx2 and y2 two orbitals relies on x and y orbitals. Okay. These are total 5 orbitals. The in d orbitals. So we are saying the dx2 y2 and dz2 orbitals, which points towards the axis dx2y2 and dz2. These two orbitals are pointing towards the axis, isn't it? And even in octahedral complex, they are on the axis, or they are on the corners. So they're straight away, like face to face overlap of the charge or electrons are gonna happen, and that's why there is a repulsion happening between the electrons which are situated in these x2y2 and dz2 orbitals and the incoming ligand electrons or charges. And that's why these two orbitals elevate themselves at higher energy level. So let me help you out with this diagram. So all these d orbitals, okay, now when they come in the crystal field or spherical crystal field, and they are attracted towards their ligands, particularly dx2y2 and dz2 orbitals are elevated. Why? Because their lobes, the electrons are present in these orbitals, and the electrons coming on the corners of octahedral crystal or the molecular shape or coordination compound shape or complex shape, the ligands will experience some, or the electrons will experience some repulsion, and that's why as repulsion is increased, the energy increases. It's very obvious, and so these two orbitals rise in the energy. This is happening with respect to the rest of the three orbitals, dyz, dxy and dxz orbitals, which are not actually pointing on the axis, and that's why there is no much of a electron, comparatively much of the electron repulsion happening between the incoming ligand and the electrons present in these orbitals, and that's why they go in the little downward energy, or they are little lesser in energy. Thus, the degeneracy of d orbital, here this degeneracy of d orbitals has been removed due to ligand electron metal electron repulsion in the octahedral complex to yield three orbitals of lower energy, that is T2G set. This particular set of three orbitals with lower energy is T2G set, and the two orbitals of higher energy EG set. Remember, we are just calling these orbitals as T2G set and EG set. This splitting of degenerated levels due to the presence of ligand in the definite geometry is termed as crystal field splitting. This is typically called as crystal field splitting. And the energy of separation is denoted by delta O. The subscript is O, is for octahedral, O for octahedral, delta O. Thus, the energy of two EG orbitals will increase by 3 by 5 delta O, and the T2G will decrease by 2 by 5 delta O. Remember, this is just the separation all this will give total energy. These are the fractions of energy. Remember, some of these fractions of energy will come to unity or 1. The crystal field splitting delta O depends upon the field produced by the ligand and the charges on the metal ion. Some ligands are able to produce strong fields, in which case the splitting will be larger, whereas other produces weak fields, and consequently the result in the small splitting of a d orbital. In general, the ligands can be arranged in the series in order of increasing field strength. Iodide I minus, Br minus, thiocyanate, chloride, sulfide S2 minus, fluoride, hydroxide, then oxalate, water, isothiocyanate, then EDTA, ammonia, ethylene diamine, cyanide, and carbon monoxide CO. So the strongest ligand is carbon monoxide, whereas iodide is the weakest ligand. Such a series is termed as spectrochemical series. It is an experimentally determined series based on the absorption of light by the complexes with different ligands. So let's assign electrons in the d orbitals of metal ion in an octahedral coordination entities. Obviously, the single d electron occupies one of the lowest energy in T2g set orbitals. In d2 and d3 coordination entities, the d electron occupies T2g orbitals singly in accordance with the Hund's rule. The d4 ions, two possible patterns of electron distribution arises. One, the fourth electron could enter the T2g level by pairing with an existing electron, or it could avoid paying the price of pairing energy by occupying the higher Eg level. Which of these possibilities occurs depends on the relative magnitude of crystal field splitting, the delta Z0, and the pairing energy P. P represents the energy required to electron pairing in a single orbital. The two options are like, if delta 0 is greater than pairing energy P, the fourth electron enters one of the Eg orbital, giving the configuration T2G3 Eg1 electron. Now, ligands for which delta O is less than pairing energy P are known as weak field ligands and form high spin complexes. This is Ag1. Okay, so particularly the ligands for which delta O is less than pairing energy, then they are weak filled ligands and gives high spin complexes. Whereas the other case, if delta O is greater than pairing, it becomes more energetically favorable for fourth electron to occupy the lower T2G orbital with the configuration T24E0 Eg0 ligand. The ligands which produces this effect are known as strong filled ligands and form a low spin complexes. This will be your typical configuration. So the extra electron that will move into and pair it in T2G orbital itself. So it produces low spin complexes. Now calculations shows that D4 and D7 coordination entities are more stable for strong filled as compared to weak filled ligands. Now this is all true for the tetrahedral complexes. So what about the octahedral complexes? Now let's understand what is about the tetrahedral coordination entities. In the tetrahedral coordination, the entity formation, the d orbitals splitting is inverted and is smaller as compared to the octahedral field. For the same metal, the same ligands and metal ligand distance, it can be shown that delta T, now tetrahedral, delta T is equal to 4 by 9 delta 0, and consequently the orbital splitting energies are not sufficiently large for forcing pairing, and therefore low spin configurations are rarely observed. So in tetrahedral crystal field complexes, the low spin complexes are rarely observed. So now here the case is little different. In octahedral complexes, the Eg orbitals were higher in energy, but in tetrahedral complexes the Eg orbitals are lower in energy, whereas T2G orbitals are higher in energy. Remember, what could be the reason? So in tetrahedral geometries, the incoming ligand electrons or charges are not along the axis. They are actually between the axis, and that's why the T2G electrons feels more of a repulsion, and that's why these 3 orbitals feels more of the repulsion with respect to these 2 orbitals. And that's why in tetrahedral geometry or tetrahedral complexes, the energy distribution is opposite as compared to octahedral geometries. T2G goes into higher energy level and EG goes into lower energy level. Now let's understand with this crystal field theory how exactly the colors are colors of this coordination compounds happens. We have seen that the one of the most distinctive property of a transition metal complexes is their wide range of colors. This means that some of the visible spectrum is being removed from white ligand. That means something is getting absorbed. So there must be some electrons which may be absorbing those frequencies from the white light, and rest of it is passed. So the light that emerges is no longer a white light or a mixture of all 7 colors, 7 frequencies. The colors of complexes is seen as a complementary to that what it is absorbed, that we have already known. The complement in earlier sessions I have shown you that color chart. The opposite, the appearing color of that complex is nothing but due to opposite frequency is absorbed. The complementary color is the color generated from the wavelength left over. If green light is absorbed by a complex, it appears to be red. And it is very well established by spectrophotometer. You take a solution of this complex or even a solid complex and pass ultraviolet and visible light from this solution samples or the crystalline samples, and it is very well observed that if green light is absorbed, then the complex or the solution color is seen to be red, or it is apparent as a red solution. So these are few examples of colored complexes. The color of light absorbed by the first complex is somewhere around 535, and that is yellow light. So opposite to that, you will see the color of this complex or solution in a violet. Similarly, if color copper complex, if it absorbs around 600 nanometers, that is red light, then the complex solution shows a blue color, or it appears as a blue solution. If this particular complex absorbs somewhere around blue light, 475 nanometer, it appears to be orange in color. Alright, so the complementary colors are observed. The color in coordination compounds can be readily explained in terms of crystal field theory. Consider the example of complex TiH2O6, the last one. Here the titanium oxidation state is +3, and there are 6 water molecules attached to the central Ti atom or ion, which is violet purple in color. This is an octahedral complex because you have 6 ligands coming towards the central atom. So it is an octahedral complex where single electron in 3D one system. Remember this Ti3 plus ion has electronic configuration 3D1. Only one electron is present in the 3D orbital. In the metal d orbital is in a T2G So we have to have this particular system there as well. So we have only one electron in 3D system, and that's why it will go first into T2G level in the ground state of a complex. The next higher state available for the electron is empty EG level. So this is your next, all these three orbitals, the dxy, dyz and dxz, all are at same energy level. So the electron can move in these systems. That's not a problem because they are at all same energy level. But for this energy, for this electron to absorb a light and get excited, you have to have it has to be transferred into EG level. So that one electron is moved from T2G1 to T2G0 EG1 level. So one electron is moved from this level to EG level, and so in excited state the electronic configuration becomes T2G0 EG1. So in excited state your configuration becomes T2G0 EG1. This is excited state electronic configuration. Now consequently the complex appears violet in color. The crystal field theory attributes the color of cooridination compound to D to D transition of these electrons. Let's say you have a ground state electronic configuration, one electron in T2G level, and when light is incident on this particular solution or a complex, this electron absorbs certain amount of energy, and the allowed amount of energy is the difference between these two levels. So it is important to note that in the absence of light, crystal field splitting does not occur, and hence the substance is colorless. When there is no light, definitely it will be colorless, but when there is a incident white light, then it will show its color. For example, removal of water from now first of all let's understand this violet color of or purple color of this particular complex is due to that electron from this ground state absorbs the energy which is equivalent to 498 nanometer of wavelength, and with that energy it gets excited, and so you observe the purple color because it is absorbing blue green kind of a color which is of 498 nanometer wavelength, and that's why it appears to be purple in color or violet in color. Now a removal of water molecules from this particular complex on heating renders it colorless. If you talk about this particular complex, Ti H2O6 Cl3. So this particular complex, when you heat it, you remove this particular water molecules by heating. Then this particular compound looks like colorless. So that means the purple color is due to presence of these ligands, and that splitting is happening due to presence of this, or this energy level splitting is happening due to presence of these ligands. Now, similarly, anhydrous copper sulfate is white, or it shows colorless. But when it forms a aqueous complex, or CuSO4 5H2O, it shows a blue color. Here, like this, it shows a blue color, because definitely it must be absorbing a red light of 600 nanometer. Now, what happens in this particular complex, the copper aqueous complex? It's basically 4 water molecules are attaching to the Cu2 plus ion. Now, these 4 H2O molecules split the electron, the d orbitals, degenerated d orbitals in this fashion, and so you have this splitting Eg and T2G. So whatever number of electrons remains in the copper ion, they get excited to T2G level, and so that energy gap is of equivalent of 600 nanometers. Remember, you can convert wavelength into frequency into energy. Remember that conversion. What is the formula for conversion of energy into wavelength? E equal to Hc by lambda. So you can easily convert this particular energy, this particular wavelength into energies using this formula. So, and it is very well explained as well, or experimentally it is shown equivalencies. The influence of ligand on the color of a complex may be illustrated by considering an example of NiH2O6 2+ complex, which forms when nickel 2+ chloride is dissolved in water. NiCl2 is, when it is dissolved in water, it gives the hexadentate complex, H2O6 complex. If the didentate ligand such as ethylene diamine is progressively added in the molar ratio of En to Ni, the ethylene diamine to Ni, in 1:1, 2:1, 3:1 ratio, the following series of reactions are associated in a color change. So you are basically replacing the water molecules in the complexes, and so the coloring is also changed. First one, when you replace two of the ligands or one of the ligand with ethylene diamine, two of the water molecules from this complex, the green solution appears to be pale blue. When you add another mole of ethylene diamine, the solution turns to purple. And then if you replace all the water molecules with addition of extra 1 mole of ethylene diamine, it gives a violet color. So by subsequent addition of 1:1, 2:1, 3:1 ethylene diamine, the stronger ligand, the color changes from pale blue to violet. So this way we can say that the ethylene diamine over here, ethylene diamine is a stronger ligand as compared to water, and this is true for this series as well. In the series we have already seen that ethylene diamine is a stronger ligand than the water, and so it's happening in these subsequent reactions. Now, in some gemstones like ruby, the color produced by electronic transitions within the d orbitals of the transition metal ions occurs frequently in everyday life. Particularly take a case of ruby, which is aluminum oxide containing about 0.5 to 1% of chromium 3 plus ions with D3 electrons, which are randomly distributed in positions normally occupied by Al3 plus. We may view these chromium species as octahedral chromium complexes incorporated into alumina lattices. The DD transition at these centers gives rise to the color. In the emerald, particularly, chromium 3 plus ions occupy octahedral sites. In the mineral beryl, the absorption band seen in the ruby shift to longer wavelength, namely yellow, red and blue bands, causing the emerald to transmit light in a green region. Now, we have seen, the crystal field theory very well explains the formation of complexes and their respective colors and how exactly it happens and all. But there are certain limitations to crystal field theory as well. The crystal field theory is successful in explaining formation of structures, colors and magnetic properties of coordination compounds to the greater extent as compared to VBT. However, from the assumption that the ligands are point charges, it follows that anionic ligands should exert the greatest splitting effect. The anionic ligands actually are not found at the low end of the spectrochemical series. Further, it does not take into account the covalent character of bonding between the ligand and the central atom. These are some weaknesses of crystal field theory, which are explained by ligand field theory and molecular orbital theory, which are beyond the now we cannot actually discuss these theories here in this chapter, so to say. Now let's understand in a further sense, let's understand how are the bonding in metal carbonyls happens. Before that, let's take a break 5 minutes.